we left off in the middle of 6.1. We're actually fairly close to being done. We left off on this previous screen discussing the idea of being able to find a number between two numbers. We talked about how sometimes with rational numbers it's really easy, and sometimes it's just not so easy. And so we have this theorem 6.6 that tells us one way to do that when it maybe isn't quite so easy. And you take a look at the next slide. We're going to do an example. We have the number 33 over 427 and 34 over 427, and there isn't any space. It's on the same denominator. There isn't any space between those two numerators, right? So this is definitely one of those that's eligible for being able to fix in this other way, use this other theorem. So what am I going to do to find a rational number between these? What that theorem 6.6 tell me to do? Add the tops. And add the bottoms as the new denominator, right? Now the nice thing about this theorem is it's not addition of fractions, although we'll get into that in section 6.2. It's addition of the numerators and addition of the denominators, right? Okay, it didn't ask me. Is there anybody in this class today that wasn't here last time? Okay, good. All right, so what is 33 plus 34? 67, and the denominator 427 plus 427? 854. And if you wanted to check to make sure that it really was the same sort of visual representation with numbers that are a little more comfortable, you could turn all three into decimals and you'd be able to see that, right? Sure. Okay. So this is one way of doing this. Now, here's example 6, the kind of question maybe that if you haven't used this book before, that you would expect to see in the connection section at the end, all right? So it says, why must there be a number between these fractions? We found one, but why must one exist? Say again?
So the theorem.
And there is a theorem that talks about it. Think about from maybe a number line perspective. Why must there be a number between 33 427 and 34 427? About this last time. Right, it's actually because it's not so much infinite, although that's a true statement, it's about the density of them, right? And that was a theorem that Kayla was referring to, the idea that there's always something between them. And if you think about from a number line perspective, so imagine what happens if you've seen a graphing calculator before, you've got a zoom capability, right? You have zoom capabilities on, Word documents and stuff too, and it makes things enormously large or very, very small. So imagine if you were able to take the number line and you were able to sort of zoom in. At some point you'd be able to zoom in far enough that you'd have a 33 over 427 here and a 34 over 427 here, right? If you zoom in far enough, you can see that even though the numbers are awfully close together, there's space between them. And if there's space between them, there's a number between them. Does that make sense? That's exactly what the whole density business means. It means that there is a number between them because there is space between them. Thank you. Did everybody sign in?
No, take more. Sorry.
I've got 300
Great.
already. Okay, so he's good. I don't have Emily on here, but I can put you in. It's okay. Yeah, I'm seeing what you were saying. It's okay. I got you. All right, so why must there be a number between these fractions? Somebody say it in words you'd like to use for me. I've given you lots of words. What could you say?
There's space between them.
Okay, so how about I use the word distance, just so it sounds a little bit better? Okay, so there is a distance between the two values. Thus, there is a rational number, just say between them. And let me put in parentheses, the word that we're actually looking for is the idea of density. the density of the rationals. Has anybody ever seen the movie IQ? Movies, nobody ever seen it. I'll have to label. Okay, so it has Meg Ryan in it and Tim Robbins. And she is Einstein's granddaughter. And she's a brilliant mathematician, but obviously during that time, women didn't do that sort of thing very often. And so one of the things, he's a mechanic. And she talks about wanting, he mentions wanting to dance with her, and she says it's impossible. Because anytime that he takes a step half the distance between them, there's still half the distance left, so he'll never get there. And he's using this idea of the density of rational numbers when she's describing it. She's using it, this idea that there's always space between them. Okay, so that's actually an example of density in that movie. All right, so a couple more connective kind of questions so you can get a feel for how these look. A student simplified the fraction m plus n over p plus n into m over p. How would you help the students? You're going to encounter quite a few questions throughout the semester that look a little bit like this, where they show a student doing something that's not correct, and then ask you, how would you help them? So there's several things you want to think about responding to when you respond to the student. The first thing is, they did something that's legitimate, right? But not in the right context here. So you want to emphasize their thinking as being good or correct under certain conditions. That's a good thing to do. You're correct if it were this, or if the problem had been like that. So that's one thing to think about. Another thing to think about is you have to understand why that doesn't work. And a why that doesn't work kind of response often works nicely if you give them an example of when it doesn't work. That is, put some numbers in there and show them it's not going to work if you put these numbers in there. So if it doesn't work with these numbers, it's not going to work in general. Okay? So those are some kind of things to think about. So first off, and of course you have to understand that they are incorrect, correct? I use the word correct there. That's really weird. Okay. So this is not correct what they did. What were they thinking that was correct? Yeah, they're thinking of sort of canceling something out, which is legitimate under what circumstances, if there were multiplication. So let's actually say something like that to start with. So first, if it were mn, and you can put the dot between there, a multiplication sign if you prefer, and pn, this idea of canceling would be correct. And the reason it's important to mention that, especially if you were telling this to really the student that was doing it, is to reaffirm that they remember something correctly. It wasn't like they just pulled this out of nowhere. Because otherwise, if you're just saying that's not going to work, then when the time comes that they want to be able to do this in the right circumstance, they're going to sit there and think, she told me this wasn't right. You see the problem? So if you don't emphasize when that sort of process that they were doing really does work, we're kind of defeating a lot of the things we've already done. So that's one thing. All right, so then let's say, but for addition, this idea won't work. And then we're going to give an example. For example, you have to be careful, because you could by accident exactly create an example that does work. Be careful. It can happen. So let's create an example. Most of them aren't going to work. So somebody gives me a value for m. We'll see if it works. What, 4? Okay, how about for n? And for p?
6.
Okay, so we're going to compare this fraction to the fraction 4 over 6. And if it doesn't work, we're going to erase and we're trying again. Okay, because we're looking for something that's not going to work. Because in general, you guys know this doesn't work, right? So we want to make sure we actually give them an example that shows that it doesn't work. All right, so what is 4 plus 3? And 6 plus 3? 9. And 4 over 6 also actually reduces to what? 2/3. So we look at 7 over 9, and we look at 2 over 3, and we say that they are not equal. And that's actually what their claim was, is that we would have been able to say that these are equal if I could simply cancel out those 3's. So we created a concrete example where this doesn't work. Now, one other thing to sort of make mention of, and you want to be able to say is, okay, so I said 7/9, it doesn't equal 2/3. I should put that not equal there. That this does not equal 2/3. How could you justify that it doesn't equal 2/3? Cross multiply would be a great example, right? So we could cross multiply should they are equal. We have a theorem that says that they should be if they were, right? How else could you do it?
Common denominator.
Get a common denominator. Get a common denominator, which is really nice in this particular one. Good job creating a great example. If you got a common denominator, you can see very quickly that this isn't going to work either, right? What else could you do? I agree. So think about really low level working with, the really introductory sort of issues with students. Diagrams are great. Because if I can draw a picture and divide it into 9 places and shade in only 7 of them, and if I can draw a picture of 3 of the the same size picture in 3s, divided into 3s rather, and shade in 2 of them, it becomes obvious without a shadow of a doubt that when I look at them, they don't match up. Okay, so that's actually a really helpful way to do that too. So any of those would be legitimate ways. So let me put the comment here. Then verify why they aren't equal. And you can use any of those varieties that you mentioned, and there's probably others you can use as well to show why they're not equal. Okay. All right, last example. If we take a set of numbers equivalent to 1/3 and graph them as coordinates or points on an xy axis, so the numerator is the x coordinate and the denominator is the y coordinate, what type of graph do we get? There's a lot of math jargon in here. But the first thing it says is we need a set of numbers equivalent to 1/3, right? So let's actually create some numbers equivalent to 1/3, which is something we've already done. So 1/3, what else? What's a fraction equal to 1/3? 2/6 would be fine. Let's do one more. 3/9. Okay. Let me do one negative actually as well, just so that we can see the other side if it's negative. I could also do -1 or -3, right? Okay. So what it told us to do next is it said, graph them as points on an xy axis. So the numerator is the x coordinate and the denominator is the y coordinate. So we're going to take 1/3 and we're going to create an ordered pair out of it. What are the points in my ordered pair? 1 and 3. So I've got the coordinate 1, 3, and then 2, 6, and then 3, 9, and then -1, -3. And it wouldn't matter what you pick. So if you didn't pick these 4 and you pick something else, you're getting the same picture overall when we're done. All right, so the next thing we're supposed to do is we're supposed to get a axis that shows it. So let me play with this just a second, see if I can remember where it is. Yeah, I did. This will just make it easier. Okay, don't do that. This will make it easier for me to graph so that I don't have to do it myself. Isn't that nice? Handy. All right, so we're going to graph the ordered pairs. So a few things to remind yourself. The horizontal axis is which one? X, and the vertical axis is Y. This one's the positive side, that's on the right, negative's on the left, positive on top and negative on bottom. All right, so my first order pair is 1, 3, and again, this is X and then Y. So we're going to go over 1 and up 3, and we're going to plot the point here. And then I have 2, 6. So I'm going to go over 2 and up 6 for my second pair, my second point rather. Then I've got 3, 9. So I'm going to go over 3 and up 9. And my last one is -1, -3. So it's down here. All right. What do you think I'll do next? We're going to connect the dots. We're going to draw the line. That's right. Let's see how well I can draw it. No promises. All right. More or less like so. So it's got a line, and it would have continued on to the right-hand side as well, but you can see that my graph wouldn't draw very well if I did that. So we have this picture, and the question asks us, what kind of graph do we get? So what kind of graph do we get? This is a what? A line. Thank you, Marissa. Yes, this is a line. Let's describe this line for me. What do you know about this line? Okay, it is diagonal, but what do we need beyond just the word diagonal? Something with a slope. With a slope of what? Remember?
2.
Close.
3.
It's 3. So remember, slope means you go, and it's positive. That's right. Go to the positive. All right. You feel it? Okay, so wherever you start, and this one actually, we could start at any one of the points that I plotted. Let's say we start here. The way you do slope is you go up a certain amount and you go to the right a certain amount. So we would go up 3 and to the right 1. Or if you went down 3 and to the right 1, that would give negative slope. So this is a line with a slope of 3 with one exception. There is an error with describing this plain old flat out as a line. There's actually something on this line that we don't have. We contend that there's not actually a point right here. Why not? Why is 0, 0, which is what it should be, not a point on this graph?
Because it's
Not equal to
close.
what?
Not equal to 1/3.
That's
It's
right.
close.
Right, so 0, 0 is excluded. Because 0 over 0, okay, that didn't look very good. Does not have that 1/3 ratio, does it? It's the only point on the line that won't. So we do have one point that gets excluded. Otherwise, we're good to go and everything gets included. Any questions on that?